Hey, hello there, and welcome back to Advent of Code, day 23 of 2023. I didn't notice the correspondence of day and year before, but yeah, this is the third session for this daily puzzle, and it's been a hard one, and we still haven't cracked part 2. But yesterday, what we did was to change the algorithm that we were using to first build a graph for this maze that we are walking along, and actually building the graph turned out to be a bit more complicated than what I expected, and it's quite horrible code, but I think we got it. And then we changed the algorithm to find the longest path to just work with this graph. And this thing made part 1 run way faster, but part 2 is, well, not running fast enough at all. We can run this, I think, with a sample, and it works. It gives us the correct answers for part 1 and part 2. We have a bunch of noise here on the terminal. But if we run it for the input, it won't finish because part 2 is just not working. So let's put a 0 here and run it with the inputs. This is the answer for part 1. It's correct, and it's not taking too long to run. Actually, if we time this, this debug thing was something that printed the maze before, but now it's not working. But if we time it, okay, it takes, no, that was the sample though, with an input. Yeah, 10 milliseconds for part 1, it's nothing, but part 2 apparently makes it so much more complicated. And well, there are two things that I would like to try out in this session, or mainly one. Basically change this algorithm to find the longest path to be something that makes more sense, because right now we are doing something that doesn't make any sense, which is to use a k-shortest path algorithm for finding the longest path. Basically, we are trying to find every possible path going from shortest to longest and then keeping the maximum of them. So that doesn't make much sense, I think. But I haven't found, well, at least not in this pathfinding crate, I haven't found any longest path implementation. So we are going to have to try to do it on our own, and I have some ideas of how to do that. But before doing that, also, I think the graph that we are building for part 2 is probably not entirely correct. So let's go back to this. We're gonna work with a sample, and I want to print the graph that we are building because I'm pretty sure there is a dumb bug here. Let's run this with actually not in why does the terminal not respond? Okay, if we search for sample, I want to just run this in debug mode for the sample. Okay, well, it seems like it is activity time for my cats, and they are running around and jumping on things, which is always nice for for being focused. So okay, here we are printing the graph that we are building, and this is actually quite noisy because we are doing part 1 and part 2. So let's also print an empty line. Okay, so this would be the graph for part 1, and the graph for part 2 is bigger. It has more nodes, and it also has more connections. Like the graph on part 1, look at this. These nodes are interesting. This is, for example, the starting node that goes to only one node. And this is I don't know, some other node that just goes, I don't know why this exists. 13, 13, let's take a look here. It would be line 14 because 0 indexing, and column, I'm watching the columns here, 14 is this intersection. So this intersection, it's interesting. It's we did something wrong here. So there are at least two bugs with how we are doing this. So this intersection goes to, on part one, we take slopes into account. So this you can come to this intersection from the top or from the left. Let's bump the font size and show the graph. Can I scroll in a less stupid way here? No, because software. Come on, how do I scroll? I can control scroll apparently, but let's run this thing with cargo being quiet, and there we go. That's the thing that we that's the graph that we are building, and the 13, 13 intersection, it says that it only has one path that goes to the exit, and the exit is this 21, 22. It's this node, but it should be two, because we can come from the top or from the left, and we can go to the right and down. But if we go right, for instance, we follow along. Here is an intersection, but we cannot go up on this intersection. We can only go down, so it doesn't count as an intersection. And we are not adding any node for that on part one, because it's basically like one single path. And then we keep going, and we go to the end. And the same happens if we go down. So we go down and down. This is an intersection that forces our way. This is the same, so we end up like either going right or going down. We end up in the same place, but we shouldn't. I mean, or maybe we should put only one. It's weird, right? It's like in a graph, this would be like two nodes connected with two. It's not vertices, is connection. How do you say in English? Like graph, nodes, and what is what I'm edges. Okay, that's what I wanted to say. Edges, arista in Spanish, but yeah, it would be like having two nodes, this 1313 node and the end node, connected with two edges, which would be the two different paths that you can take to it. But that would be what I meant to do, but I screwed it up because I'm using a hash map as the container of edges, and that means we cannot have repeated keys, and that would be because we are having the key as the node itself, and the value is the cost. So either we have to keep both of those edges in here, or at the very least we should keep the maximum, because we are interested in longest paths. So that's one thing to fix. Let's actually take note of that. I have another note to do, which is to report it back to the library that we found on a previous session. But what was this? Keep repeated edges with different costs on graph. I don't know, something like that. And I wanted to look at the sample. We can close other things. Okay, so that's one thing that I wanted to fix. I didn't notice before that that was there, but also there's another bug, not just one, but two on this graph generation. It's working for the sample, it's giving the right answers for the sample, but maybe it won't work for the inputs because it's doing things that I didn't expect to do. So on part 2, it's basically the same as part 1, but you don't obey the slopes. So basically, if you fall into this intersection, you can go whatever direction you want to go. You have 4 directions to go. Like it doesn't matter which way you come in. But when we are building this graph, we are ignoring, like basically if we come to this intersection, for instance, from the top, we are only saving like the left, down, and right directions, and not the top one, like, because we are assuming we cannot come back, which is true for a given walk, but you can consider another, maybe like that is the walk that we are doing for building the graph, but then for computing what is the longest walk, we are going to traverse this graph in like many different ways, and maybe the longest walk consists of coming from the left, for instance, and going back from the top. And we are not going to be able to do that if we don't put that on the graph. And you can see that on part 2, actually here, the first line on the part 2 output is this 1313 node, which is the one that we were looking before. But this is when we are building the graph for part 2. And you can see actually it doesn't connect to the end on part 2 because there are other intersections first. That's also interesting. But there are 3 edges when there should actually be 4. So that's also another bug that we have to fix. So keep all edges on intersections on part 2. Interactions. That sounds like another thing, but okay, that's those are 2 things that I want to fix, and then I want to implement longest path algorithm by hand. What does by hand mean? Well, everything is done by hand when you program, I guess, or by the computer. But okay, that's basically the idea. And to do that, I don't know what I'll do. I'm thinking about trying out some sort of kind of breadth-first search of all the possible paths, but maybe that's completely unreasonable for the connectivity of part 2, so maybe that won't work. But first of all, we should fix the graph. Okay, so the first problem that we encounter, dead end. Yeah, this code is also so ugly. I had to disable a Clippy warning here too. Like it's a mess. It's a giant mess. Look at this initialization of the graph. Let's at least put this in a nonsensical order. But where are we doing this thing of, like, okay, like even the representation of the graph. I changed this for some reason on the last session, but I don't exactly remember why. Like instead of using vectors, like a linear vector, I did something else. But, well, I don't remember why, so let's pretend that I didn't do it for a reason, or that maybe that reason was not good enough. It's no longer valid, so let's change this back to using a vector. And what are we doing? Okay, when we find the end, we push this into the vector, so that's gonna be very similar. We push. We should also here. What are we doing? We are unconditionally saying, hey, you. This is basically the match. This is the condition of what we do in different cases of neighbors that you have, of possible neighbors. So you can have, well, a 0 means a dead end. Basically, when we are walking along, and this dead end should only happen on the when you're coming back to the start, which sounds like a Coldplay song, but also is something that we shouldn't be doing. Maybe like Coldplay, but no, actually, it's a nice band. But we're doing this because we start from the start, we come into this intersection, but then for part 2, we are looking in every direction and we are going back to the start, and then we stop iteration there because we already know about the starting node, so that ends the iteration. But is it okay to do this? I will assume that this is okay. I'm not entirely sure. I think I remember now we're having more repetitions than we should have. So maybe that's something. I think I'm remembering now. But let's ignore that. Then we are going through all the directions that we have neighbors to, that we can walk to, and then we're saying, hey, you can go from initialize this, and we are initializing this because we are also early terminating somewhere. I don't know where. Or no, it's okay, we know. Why are we doing this? Contains. Oh, this is just an if, then it's the for. It was confusing. I thought that this was inside the for loop and it didn't make much sense. Here we are saying, okay, graph, you can connect this node to this, and this is the amount of steps that it takes. And this node position is the position where we're starting this walk. Yeah. Okay. So that makes sense. Then we are saying, okay, if it didn't contain this key, now it does. So this is basically the termination. If we already know about this, if we have walked to X, Y, and we already knew about this intersection or this node, we don't do anything else. So that is the way we cut extra walking, this if condition. And then we say, okay, we know about this. So here, instead of a new hash map, it should be a new vector, sure. And then we are pushing new things into the stack to process, starting from this XY and going to each neighbor position that we can walk to, which makes sense. But if we run this now with the vector, I think we are going to, well, we have some compilation problems. Where are they? Oh yeah, when we are iterating, what do we want to do here? So nodes is reference to a vector, and these are not references, I think. And what are these? Yeah, I'm pretty sure that if I just dereference this, now dereference here, It's gonna be fine. Yeah, okay. So we can actually like change this to, I don't know, entry. And actually look at Clippy, considering using the copied method. Yeah, thanks Clippy. Okay, great. If you run this again, we still, well, we get the correct answer for part 2, but not for part 1. We screwed something up there. Like, not cool. So how does the graph for part 1 look? Well, now we have the two ways from walking from 1313 to the end. One takes 25 steps and the other one takes 33. It's like, okay. But how is it that now part 1 is giving a bigger number than the... That's curious, right? I was not expecting this. So let's maybe compare. It would be nice to use some graph layout library to take a look at how these graphs actually look. So, like seeing just numbers of edges is not the best way, and also it's extra complicated also because we the iteration of this thing is like the order of iteration is not consistent because hash maps in Rust don't have a consistent order of iteration. It's a feature, not a bug, but sometimes you want that. So why could it be that we are having now a problem with that? Maybe no, we are doing this ensure thing still. Found too many paths. So before, for instance, on 13 we had this. So the number of things, we had 5 nodes in total. 2 of them had one neighbor, and the other 3 had 2. And now we have also 5. 1 still has 1, and the other 4 have 2. Like we have, and it makes sense that this has 2. Like I think it does, but it went from 94 as the minimum path to 119, which should be impossible. Like, what is this thing? I think I should print it probably and find out what the hell we are doing. It's not gonna be very pretty, but it's gonna be something. And also I want to, when we iterate this thing, I want to iterate in order. So let's have this thing sorted. If we just say sorted, yeah, look at that. Thanks, itertools. If we run this like this, still the same answers, but now the order of iteration should be consistent, and that is useful, I think. We should always see the same thing. That's great. And this can be sorted even though the iterator is over key values, because key values are tuples, and tuples are ordered if the elements on them are ordered. And yeah, these things are all like vectors and tuples and blah blah blah, so they are all lexicographically orderable. So that's nice. That's nice. So what I want to print is this longest path that we found. It's not going to be pretty like before that we were printing the grid, but we should be able to follow this. Longest path is, well, the longest path debug mode, and I actually, well, let's print it like this. I think it's gonna be a bit noisy. No, it's not too noisy actually. Oh, because it's not giving me the costs. That's cool. So, okay. This is the longest path for part 1, and this is the longest path for part 2. Surprisingly long, the one on part 2, but no, it's not surprising that, because, and actually this one is the correct one. We know that 154 is the output that we want. So this is what we are expecting, but 94 is what we want for part 1. So what is it doing? It's going from, of course, the start to 3.5. So where is 3.5? Let's try to follow this along. I can make it this shorter, right? Can I see something here? Am I able to see? It would be nice to be able to scroll with. Yeah, there you go. This is what I want to see. To scroll like by one line, but I don't know. The scroll wheel is not doing that. It's probably something that can be configured. But anyway, I bet that this is 3.5. It looks like it. Then it's going from 3.5 to 5.13. So that is 5 on X, 13. It would be this. So it went down, it seems, which is okay. It's valid. We come here. Great. First of all, is there anything repeated here? It shouldn't repeat any nodes. That would be a bug. But okay, we are in 5.13. Then it goes to 13.19. So 13 on the X and 19. So here it can go right or down from this intersection. And it went to 13.19, which is this one, I guess. Is this 13? Yes, column 14. So how did it come here? It came here, it went down. From here it went down. Maybe I should record the directions in the notes to make it easier, but okay. We are on 13.19, then it went to 13.13. That doesn't seem possible. So how did it do that? How can it go from 13.19? Oh, this is... Oh, I was following part 2. I'm an idiot. It is possible in part 2. Because it's going up, I think. And I think it's going here. Yeah. But that is fine on part 2 because it came here up again. But I should have been following part 1. So, okay. Part 1 goes also to 3.5. So we are here. Then to 11.3. I'm an idiot. So it seems like it's turning right, it's going this way and all the way here, and this I bet is, yeah, then it is on this intersection, 18.13. Here it can go right or down, and it's going down, I think, to 13.13. So it's going like this and like this and like this. It ends up at our known 13.13 thingy. And here it's going to, what's happening here? It's going to 21.22, but now we have, that's the only thing we changed. We now have the two paths, but is one of these paths something that we shouldn't be able to take? Because one of them is longer than the other one. But I think both of them should be valid for what we are doing, right? What's the problem? Like, what's the actual solution for part 1? Oh, it's kind of ugly to see, but here the actual solution goes to the right on the 13.13, and it makes all this way whereas if we go down, it goes like this, and yeah, this one does look shorter, but then yeah, it took right there, and here it went down, which is, it seems to be what we were doing. So why is this suddenly different than when we were using the hash map instead of the vectors? Like, the only thing that I can think of is there is a new connection from 13 to this, which should be longer, but we should have always been taking the longest one, I think. Although let's take a look at that. From 13 we now have either 25 or 33 cost. So one is longer than the other one, sure. But the difference between our answer now, like, okay, the difference between 25 and 33 is 8. And this is not the difference that we are seeing. So it's not just that. How can it be this long? What are we counting here? I am confused. I am quite confused. And before, when we were using the hash, do we still have that? Yeah, here we have that. We were keeping only the longest of them, and this was working. Are we double counting something? I don't understand. How can this... Like, it seems such a trivial change to do. What did we mess up here? Okay, we changed this. We just changed some inserts for pushes, that's all. That is all. The notes here, yeah, they make sense also. So what's going on? What is going on? When we push something with the cost, like, okay, we reach here, we push, we could push only if it didn't exist, or overwrite the one that exists and put the highest value. But I don't see how that could change the, like, how is this giving us a different answer? Really, I don't, I feel kind of stupid now. You know what, let's comment out of part 2. Let's have a simpler output for part 1. Okay. Okay, and let's now revert the stupid thing that we did and go back to a hash map and see where we go wrong, because I don't understand. Hash map, new. This is now, this seems like a very, like, sorry if anyone is watching this, because it looks kind of stupid, but that's how I do debugging. And this should be a hash map. And you cannot sort this. Why? Because it's not satisfied. because I mean, don't you want to be sorted? Can't you sort it somehow? K and V, and if we dereference, one thing that I would like to know if there is a kind of like copied method, but one that would do exactly this for tuples. Okay, let's not fret about that. I think we can use this is a sorted iterator. Can we just sort by key? Yeah. Okay, and instead of doing that, what we were doing before was something kind of like annoying, but kind of like this, I think. K and B. Okay. And is that it? Lifetime, blah, blah, blah. What are you? Double reference, like double D reference, and don't bother. Okay. If we run this now it is the correct answer. And what did change? Did some of the weights change or anything? The only thing that I see is that we have a new path here. But the other ones seem... Oh no, look at that. 513, here there's a 53, what? To go to the end? Oh no, it's here also, yeah, okay. So you can go directly here to the end, but that's not the longest path. But everything else looks the same. So what the hell? What the actual hell? I guess the difference that we are adding a new path here is, wait, 94, this minus this is 20, yeah, it's 25, it's the weight of this thing, so it's, what? It's like adding these two weights. Oh, that's not right, is it? It's adding the weights. That doesn't sound right at all. Yeah, but that seems to be the problem. So, not great. And it has to do with this k-shortest path work, I guess. But okay, like, does it make sense to have this on the graph at all? I think if you have two paths to the same node and one takes longer than the other one, we should only keep the longest one for what we are interested in. Here I was thinking of, okay, let's keep all because that makes more sense in my head, like, but you can also, like, this build graph is only for this problem of finding the longest path, so we can think about that. Although it's kind of annoying that this thing doesn't recognize that. So okay, that was going back to the hash map, and now we understand what's going on. Let's go back to the vector. Back. Come on. Okay. And yeah, back to everything. Something else? Yeah, print the longest path. I don't care. Okay. So does it make sense still to, like, is this the graph that I want? I'm not entirely sure. So now that we went back to the vector, we should be having the wrong answer. We're going to change this longest path algorithm nevertheless, so I wouldn't care about that for now. But we know that part 1 is now having a wrong answer. Now about the graphs for part 2. We want to fix how the graphs are generated. This 1313 should have 4 connections, and we are not doing that. And we are not doing that because of how we find these neighbors. Basically, the neighbors, this is an iterator over all the directions, and we compute the position on that direction. We filter out of bounds things. This is fine. And then we do this other check of, we want the direction that is basically going back to where we were coming from. We also filter that. And then we also filter depending on walls and on slopes. This makes a lot of sense. That's how we walk in this maze. And then we check how many of these valid neighbors we have, because this is basically, we are keeping the position or none if it's not a valid neighbor. So then we just count how many of them are, like we filter if they are some, basically. There's probably a better way of doing this. Valid neighbors, like, because we are not using neighbors, this is kind of unnecessary to do like this. And we can get rid of this extra variable if we just do a filter map here, right? We can do that, and we just use the neighbors here. I think. This should be the same, or not, because what did I change here? Did I change like the iter? It can be, they could be mapped, but not filter map? Why is this? Oh, because, okay, it did make sense, I think, what we did, because I don't want to be recomputing this every time. So neighbors is not an iterator, it's a static array. So yeah, let's leave it at that. Valid neighbors is fine. Valid neighbors is fine. But I think we want to get rid of this check here of it being the previous position, because we want to consider that for building the graph when we get to some to some intersection. It's kind of complicated, right? Because if the previous is a slope, then it's not so easy. It's not so easy. We have the condition of this being slippery slope. So this is basically if it's part 1 or part 2. In part 1 the slopes are slippery. So I would let's sketch it out. I would remove this from here, and then it's basically one more than we have. 1 would be this case, 2 would be the case that we are walking sort of in a tunnel, and then it could be more. Like 0, but 0 cannot ever be, I think. Oh, and it's this is interesting. No, the slope checks will take care, I think, of not going back in the case that we are checking slopes for part 1, which is nice. So we are going to return on there, and so this is not just the dead ends, I think, then. Let's look at the sample. So for instance, on part 1, when we reach here, we should have 2 neighbors. And we cannot go back, and we can walk to either 2 of them. Okay. It's kind of more complicated than I thought this would be. How on part 2, like the complicated things are things like this, when you can reach and you can go from multiple ways. Should we just say something like having trouble thinking about this. Again, like walking a maze sounds simple when you see it visually, but then you want to code it and you realize that you're a visual animal, basically. Look at that, preview pose is never, it's never red, which is not good. We should take care of that. We don't want to go back. We don't want to go back when it's a tile, basically. We don't want to go back when it's dots. But if it is, like, what's the correct logic for this? Maybe I'm I'm overcomplicating things because I'm trying to do this same thing for part 1 and part 2 with like some conditional, and maybe I should have one thing for part 1 and a completely different thing for part 2. But basically, on both parts, when we reach an intersection, we should be seeing multiple ways that we can go. Here we are not filtering then the previous one, so now to keep walking, we should do something. Okay, if we see 2 valid neighbors, we should take the only one that is not the previous one and walk that way. right? And that is if we see 2. But sometimes, like on part 1, we would also see 2, like we would see 2 if we are walking here, like the previous one and the next one, but we will also see 2 in a case like this, where it is actually a bifurcation. So it's not really that simple, I think. What I want to do then is not really it's not exactly like this. It's like, okay, you can walk. We have these neighbors, which is, let's say that these are the things that you can walk to. Yeah. Let's divide this thing a bit further. So these are the walkable neighbors, right? And then what we want to check is how many of the walkable neighbors without the previous one. I think that should be it. And these are valid neighbors. Yeah, let's say this will be walkable, but not priv neighbors, or like, I don't know how to call this. Let's map these. Yeah. Walkable non-previous neighbors. A horrible name, but let's be explicit because I'm having trouble thinking about this. And it's gonna be a very similar thing. We want to map these things, and what we want to just filter out when is this the previous one. So we're gonna say here neighbor is already an option, so can we ask and then I think is what we want. And then takes what does it take? Give me the, yeah, it returns an option. Yeah, it's like option chaining. This is kind of what we want. So, and then here we can say xy. If this x y is actually just it's a position, right? If this position is the same as previous position, we're gonna filter it. So we want to filter out that. Yeah, right. Else, kind of a ugly way of writing that, but I think it should still be correct. Like this is the same as walkable neighbors, but without counting the previous one, right? Kind of very ugly way of doing that. Actually, like this is a very stupid way of doing that. We just want to count. We're gonna have like the walkable neighbors are right there. We know about them. do we need to have this as like as a static array? I'm tempted to just use dynamic vectors and allocate memory and forget about these stupid restrictions or of avoiding allocations and make the code easier to read simply. That might be because what do we want to do with this? We just want to count them and then maybe use it for this, for the case of this. So we are going to go back to 0, 1 in here, and we work out non-previous neighbors. And here we are, we are having an iterator and counting that. So what do we want to do? It's only one. Yeah. What are the different cases? Like if we try to extract this thing, we can have, well, either 0, dead end, only 1, or like 1 and more, let's say. Yeah, I think we can just extract that and not care. Right, okay, let's write it in a very ugly way. Like this is the thing that I want to count. So I'm just going to want to say, hey, iterate over these and filter map, kind of what we are doing here, right? Filter map like this and count. Horrible, okay. Dead end, and then for this is this what we want. Clone next, blah blah. No, actually we just want to say give me, like we know it's 1, so just give me that 1. Iter find map, and just, this is so ugly, but yeah, give me that 1, and then valid neighbors. Yeah, it's this walkable neighbors thing. So that is what we are consuming here, right? Yeah, let's just simply say, okay, we are going to go into all walkable neighbors. And now this is going to be an option, and if it is some, let some neighbor position, then we push it, and you want to look at that, you can do a flatten. That is something, so flatten you can use as kind of as a way of doing this filter map that we were doing before. Well, the more you know. Awesome. walkable non-previous position. Great. So I guess this filter map can also be flatten, right? Flatten, creates an iterator. Yeah, flattens nested structures, but yeah, okay. Sure. Okay, is this, although it's ugly, is it right? Like, right in the sense that it generates the thing. Okay, so on part 1 it seems to be generating kind of the same thing as before, and on part 2 we see that 13 is now connected to 4 places, and it terminates, so that's also nice. So I think this is, although it's horrible how we written that logic, it is kind of what I wanted to say. What I don't like about like writing horrible code is not just that it's horrible, but it's kind of an evidence that my thinking process is not clear. Because if I cannot think clearly, I cannot write clear code. And if I cannot think clearly of this, it means that, well, I'm not understanding the problem very, very well. But, well, that's sometimes what happens. We are finding only one dead end here, which is fine. It makes sense. So, okay. Now this graph making thing does make sense to me. We have sort of done these two things that we wanted to do, and it's already been an hour of a video, and I thought that those things were going to be like trivial, but well, I'm bad at estimating things. Ask my previous managers about that. Anyway, so now we want to find the longest path, and we have this horrible thing. Let's add the changes that we have done, even though they are ugly. So, okay, how are we going to do this? Let's try to estimate how many paths, like around how many paths we are going to find. So we're printing a lot of stuff. Let's comment this printing. We are also printing the longest path, which I don't care about now. Let's print other things, like let's print found paths, and it's gonna be okay, shortest paths length, which we cannot use because it's already been moved, so let's print it here. Okay, this we are no longer using. This is how many paths we are finding, and let's also print, I want to see this graph. So my intuition would be, okay, we are going to start from the beginning. This will lead us here, which we have two possibilities, so it's going to be 2 times the different paths that we can take. It won't be exactly exponential, but I think it's going to be close to that. So if I want to estimate how many paths we are going to consider, because I think it shouldn't be exactly exponential, because we have to, like, at some point when we reach some dead end or some path that we can no longer take any other path because we have already visited those nodes, we should end that iteration there, that path there, even though there might be other things that we can visit because we are just in a corner and we cannot go to other places. But it will be kind of combinatorial, kind of exponential. So let's estimate that by printing estimated, or I don't know how to call this, like graph. it's not cardinality, but it's kind of like combinations, I don't know, something like that. And this is gonna be the graph values. Then we're just going to take their length and make the product of this. And I think this is gonna need some type annotation. So let's take the product. I don't remember. It's U32, but let's take it as U64 because this might be a big number. And you don't like this because cannot be. Okay. Length as U64. Okay. Okay. So on part 1 we have 16 combinations and there were 4 paths. But in part 2 there's many like estimated combinations. But just 12 paths. So, okay, the number of actual paths that reach from the beginning to the end is going to be a much smaller, a smaller subset of these combinations. But this is what the algorithm found, so maybe it did consider a big number of possibilities, like similar to this amount of combinations. And if we do this for the inputs, which won't finish for part 2, I think, but already on part 1, too many paths. On part 1 it's already at the 33 million. But we can print this because we don't need to, like, we can put this thing at the beginning. So okay, the amount of combinations of part 2 is tremendously big. So this is a non-computer friendly big number. So that's kind of the problem or on part 2. On part 1, if you do a brute force search, it's 33 million combinations. So you could actually do, like, 33 million is not a big number for a computer. You know, it might take a second or something to process that. But basically we could take all the combinations of all these possible nodes, like, without even regarding. Oh no, you have to regard their connections, but just, you know, the combinations of them, and see which ones are, like, valid, that takes you to the end, and take the one that is the longest path, and that would solve part 1. But for part 2 it's a much bigger number, and that complicates things. So, well, I don't know. I don't know why I wanted to look at these numbers. Maybe to have, like, an idea of, this is actually a much more complicated problem now. So this is billion here, it's gonna be trillion here, quadrillion, so a quintillion possibilities. Awesome. That's awesome. So let's now put our thinking hats, because so far I think I haven't been thinking very clearly. And try to think of a way of actually implementing this. There is, let me think. One interesting thing that would be nice to, I was just thinking about something else, about like the topology of the graph. But I don't want to think like special cases. I want to like mostly think about like the general case. And then when we see that, you know, it's not going to be ending anytime soon, try to think of, okay, what are the edge cases and what can we do to avoid extra iterations, or like maybe some caching or something like that, which is always a nice optimization to put somewhere. So yeah, let's get rid of this. Let's get rid of kind of everything. Yeah, bye. Just start with a blank slate here, blank canvas. So we want to do a kind of sort of a breadth first, or kind of searching algorithm, but we are not going to end just when we reach the end. We are going to, when we reach the end, we are going to collect that result, and then we are going to take the maximum of those. Or actually, we don't need to even collect everything. It's like we can keep the maximum. So maybe let's start there. Let's say let's max path. My cat sneezed. Let's mute max path. And well, at the beginning we don't know the max path. So let's, I don't know what max path will be, maybe like the vector of paths or just the cost or something, I don't know. But we are going to have that. Then we want to have like sort of a stack or something to push and pop things into. So let's say that. Let's say let's mute. I don't know how to call this, so I'm just going to call it a stack. And how are we going to start here? Like, what are we going to keep track of? Do I want to keep track of the whole path? I think maybe so. Because or where I think we need to sort of keep the whole path. Well, let's assume that that is the case. So the first thing that we're going to do is to start with a little path that just consists of the starting node. And then we are going to do the usual while there is some path in this stack that we can pop. We are going to process this thing, and we are going to keep pushing things into the stack, like not recursively, but kind of like in a loop. Okay. So how are we going to do this then? Like, let's assume that the paths are always like non-empty, because we start with a path that is not empty, and we are always going to only add things to those paths. And here I'm going to be copying memory like crazy, I think, considering all of the different possibilities. But that's okay, I guess. So if we have a piece of path, we would like to get the last node and see what we can visit from that last node that we haven't visited before. That's kind of and we are sort of going to consider all of those things, right? That's kind of the idea, I guess. Yeah, I think that's kind of the idea, that like everything that we haven't visited before. Yeah, and the end condition, let's write first the end condition, which I think should be kind of trivial. We can say if here let's extract, let's say last node is path dot last, and this should always be present. So let's unwrap. If the last node is the end, well, we have reached the end. So we're going to say, let's first print, and we should also keep the cost somewhere, like probably the total cost somewhere. So this is not just going to be a path, it must include a cost somewhere over the rainbow. Okay, so I want to see, here we're going to continue, not break, but continue, because we can have many paths reaching the end. This thing should return a result of U32, so let's hard code this thing so it doesn't complain about stuff. So the cost, what do we do with the cost of things? What if this stack keeps paths and costs? So the first path is just the start vector and a cost of 0. And we have something like this, and we increment the cost, the cost with, no, not 0, cost. So yeah, that makes a bit more sense. Max path needs a type annotation, sure. Let's this thing be like also something like a vector and a cost, or whatever. And let's not make it optional, so we don't deal with optional thing here. So here, what I'd like to say is the last node is the end, reach the end in cost steps, and we are going to update this, or max cost, let's say, and just have this, and we are going to update it. Max cost, we're going to assign it it or the cost that we have now to reach the end, and in the end we are just going to return the max cost. So okay, we have the stop condition, but we are not using the graph for anything, so this won't do anything. We now need to, okay, if we didn't continue the loop here, we have to walk. Well, not walk in the stupid grid, but walk in the stupid graph. So how are we going to walk? Well, we're going to get the neighbors of this last node and filter the ones that we have already been through. So that should be, I think, relatively easy. Like, I think the trivial algorithm for this is going to work relatively well for the sample, but I don't expect it to work on the actual input. But let's see. Now, what I mean doing if what? Let's grab the graph neighbors for this last node, and this is going to want a reference, and let's filter. Now this is going to be a vector or something, right? The graph in the end is a vector, yes. We're gonna iterate over this. We want to filter the ones that we have already walked, so the ones that are in the path. So node, let's say a node, and filter the ones that are not contained. So path contains, if it contains the node, we don't want to go over that. But if you contain it, yeah, we will filter it out. So for each then node in this, we are going to push into the stack a new thing to process. I think should be fine, right? We're going to push a new, yeah, and it should be a new path. Here is where I'm going to allocate memory. So we're going to say let's mute new path. It's gonna be the path. There is like a concat and things like that, right? That's, what does concat do? Concat. No, it's not what I want. There's an extend and things like that. Extends from slice, but these things mutate the self. Extend, for instance, yeah. I just want to do clone this thing and then new path. Let's do the simple code. New path, push this node, and then into the stack we're going to push this new path. And actually node here is not a node, it's a node and a cost. So let's actually have node and cost here, and you can be dereferenced, and you're gonna have a new path. Oh, and this cost is different than this, so let's say let's call this thing path cost, path and path cost, and node, and let's say for consistency node cost. Great. So we're gonna have the new path and the new cost, which is going to be path cost plus node cost. Okay, and now the node is not what I want. I want to filter here again. We're going to have a node and an unused cost. So okay, Beautiful. Yeah, I'm not very. I said beautiful ironically, like I don't think that this formatting is very beautiful, but anyway. Is this, like, this was pretty simple to implement. Like, I wonder if this is enough for the sample. Woohoo, look at that. We did get the actual inputs, the actual outputs, what we wanted, and reach at the end in many different amounts of steps. Like, we did reach it many times but we are only keeping the maximum. So maybe we can print this thing like if path cost is more than max cost, we're gonna do this, and actually sort of unconditionally assign there. Now we should see, okay, when we reach 94 for the part 1 answer, and when we reach 154 for part 2. Great. And we are using less things. Okay. So yeah, this seems to be quite nice and correct for the sample input. I don't expect this to work for the actual input. But can we get, for instance, the part 1 solution? Look at that, it went... What was the... Yeah, this first thing, reach the end in blah, 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 is the solution for part 1. And then part 2 is chugging along. We have already found 6,000. So there might be bigger, but this is nice to... It was a nice decision to print the maximum because, okay, we now know that the algorithm is chugging along, and maybe there is so many more paths to... Oh, look at that! It's finding more and more. But maybe this will converge. Well, it should end at some point, I think. I don't know if it's going to end in any reasonable time, but this is already more promising than what we were doing with the k shortest path. Oh, it finished. Awesome, this naive thing actually finished. Is this the correct answer for part 2? Crossing fingers. Yes. Wow, this was a very nice lesson of... You should sometimes think on your own of how to do things, because this was not that complicated. Once we have built the graph, walking it and finding maximum path, like in a very naive way, was not that hard at all. It was actually kind of easier to think about this than using the k shortest path algorithm. Now, it did take quite a bit of time to reach the solution for part 2, but it did work, which is awesome. It's awesome. And I reckon that we can probably make some things much better. But, well, we can take a look at the advent calendar. So we have worked our way through day 23. Now we have a star here, the beautiful waterfall. So we are only missing 2 days. That's awesome. And 46 stars we have collected. Great. That's awesome. I actually didn't expect this to finish anytime soon, like to converge to an answer and, you know, have something that actually works. That's really, really cool. We can copy this and put these things on the answers file. So it is a correct solution, not a performant one, but it is a correct solution now. And we weren't even running in release mode, right? Yeah, we weren't even running in release mode. So that's great. We can remove some of this printing and noise. The dead end is like, okay, good to know, but not really important. Is this necessary? Can we say like break like this? Yeah. Although maybe it's, yeah, this wants to just be a comment dead end. And we had some other printing. This was a very nice printing to have, to see the thing working and seeing that we were actually getting somewhere. But now we can go back to, let's say, max cost max. We can go back to this idea, simplify things up, and we can now run in release mode, I think, and see. Well, it's going to take some time. Let's actually time it like this. Just build the thing and run it. It should run faster in release mode, but well, it's not a fast algorithm. Usually release mode runs like a couple of times faster than debug, but it really depends also on what you're doing. If you're doing a lot of arithmetic, it runs faster because it's not doing overflow checks. But okay, 18 seconds. It's not great, but it's also not super bad. So that was awesome. I actually was a bit worried that we wouldn't get this thing, a solution for part 2 of this thing, but we actually did. And it wasn't that hard once I forgot about the idea of using the k-shortest path algorithm. It wasn't so bad. Like, the longest path is actually much shorter and simpler code than the graph building code, which is super messy. It is super messy, I have to admit. But yeah, let's commit this. I did have, the previous commit was improve part 1 solution. It was a terrible commit message, but okay. Let's commit this like it is right now. Add day 23 part 2 solution, and let's describe a little bit of it. After building the graph, find the longest path using a naive and simple this is kind of a depth first search like algorithm. Right, depth first because we are using a stack. So okay, I think that is kind of what we did, yeah. Not a very performant solution, but it's something that works. So now if we run like check all, it's going to start taking like more than 18 seconds to run, which is not nice. But I also have another script to just check the samples. So that should be fast enough, and it is. And it's also checking this solution with sample input and output that we expect. So it's good enough. I would really like to try to not have terrible performance of this. There is probably some things that we can do, like the way that we are avoiding an infinite loop here is this filter, because we are not visiting nodes that are already in the path, which is a very basic thing to do. The path could be a hash set, for instance, or something like that, that would be a bit like simpler in terms of asking if it is contained. Not simpler, because it's also hashing, and you know, a vector is, well, it's usually more memory friendly because it's just contiguous memory. Well, the hash also has the contiguous memory, but it has to do a hash operation. Yeah, maybe using hashing and a fast hash would help. There is the fx hash that we are not using, right, in Cargo. Actually, this is something that I never... What are our dependencies? These are some nice dependencies to have. All of these crates have been massively useful. But maybe using like a faster hash would improve things, although I don't expect it to be that much better. One thing that I would like to do, I would like to know about is, let's print here, print ln, man, I cannot type for my life, graph size, I want to see on part 2 what we are dealing with. So, ooh, look at that. The graphs themselves are quite small on part 1 and on part 2, and that gives me a very nice idea. Specifically, the size is less than 64, less than the number of bits that a single word on my machine has. That gives me an idea. We could use like a bit mask to know, like instead of having a path being a vector and doing, you know, doing things that make sense, we can have the path be like, have a bit mask of the path where each bit corresponds like to one of the nodes, and have ones on the ones that you have visited and zeros on the ones that you haven't. And well, then building the paths will be much cheaper, because you're not allocating memory for that. It's just you know, not a new vector, it's just a number. But also, that also gives me the idea of like caching, because right now we are, well, we don't have any sort of cache, but we could have like a cache with the maximum costs for each path, like each intermediate path. And when we are evaluating a new path, we could access that cache and say, okay, do I know about this path already? And if I have visited, well, not the path, I mean, not the path, but like sort of the bitmap, or like the set of nodes, but not ordered, like in any order, because maybe we are going from A to B in some long path, but then we are also going from A to B, following along the you know, visiting the same other vertices, but with different cost. And if that's the case, we only want to care about the maximum of those costs. So if we know about that, not the path, but that set of nodes, and we know that our current cost, so this thing, is less than the one that we already know, then we shouldn't push this thing to the stack to process, because we know that we have already evaluated something that visited the same amount of nodes but took a longer path to do so. So I don't know actually if that's something that would happen frequently to make that sort of cache optimization worth it, but I think this is something that potentially could save a lot of time by caching. It could be interesting to do that, yeah. But yeah, I didn't expect the graph size for part 2 on the actual input to be this small. Only 35 nodes. So that's nice. Using a bit mask now is something that I really want to try. And another thing that we could do, this is not so like such a big optimization, but it's something that I would like to do, is to change the graph. And instead of using, like, change the graph that we are using here to find the longest path. Instead of using points, just use indices. Just convert all the points on the grid to single numbers and just use those numbers. And instead of using a hash map, you can just use a vector. And this would be like a vector of vectors of U size, so indices and their cost. And that would be it. And it would simplify things even further. That's a simpler thing to change, although I don't expect that to... Like, that would be an incremental simplification, and I guess it will help for performance, because it's, as you know, it would avoid most of the hashing, because most of the hashing is happening inside of here. But I don't expect that to be like a 10-fold increase or something. Like the basic algorithm would still be doing a lot of work, whereas something like cache or a technique like that has the potential to reduce the cost of this significantly, because, well, that's the nice thing about caching. It's like it's a very compounding effect, and yeah, the effect that only one cache working correctly can be enormous. But I think I will leave that to yet another sitting, another session, and another video, because it's already been 1 hour and 40 on this one. But we did get to a working solution for part 2, so I'm very happy about that. I wonder what was this Clippy warning that we had here. Yeah, I wanted to use like one of these entry thing. So is this, yeah, this gives us an entry, but it's like kind of ugly. What's the good way of asking for this? We can say entry pass the key. The key is like this thing, right? Or insert is what I want, kind of. Or default, or insert with, or insert, what does it take? Yeah, it takes a value, so I guess I would need to do something like or insert with, and then have, what does this do? Yeah, it's like, I'm not sure if this is better, you know. Like we would be inserting an empty vector in here, so it would be an empty vector, but if we are inserting, we would also be doing the for loop in here. So I think that is basically what Clippy would want us doing. What I don't like about this is like we are putting on like this kind of side effect on here, or insert with. Interesting. And returns a mutable value. Yeah, it's not something that I particularly like, but would this work the same way for the sample, for instance? Yeah, it seems to work the same way. Do I like it? I don't know. What would be another way of asking this? We could do an OR insert, but if we do an OR insert, we don't know if it is the first time or not that we are seeing this node. So, and I want to know that. So I don't know if like the get entry, like the entry thing. Oh, there is an and modify also. And modify is kind of the inverse, I guess. Key gives me the key. And modify would be like if it exists, then don't do anything. Yeah, I don't know. The previous way of doing this that we were doing, like, hey, asking if it contains the key and then inserting, is like, the problem of this is that you are doing like a double hashing to get to the thing, but it's like, whatever. I guess one thing that you can do is graph get mute. No, but this will return some, but you cannot access it if it's not there. Yeah, it's like I want to ask, and if it's not there, do this and insert something. So okay, the or insert with is kind of okay, I think. Yeah, let's leave it as this, and let's not silence the Clippy warnings, which are useful usually. And this is alright. This code is actually pretty nice, I would say. So yeah, what we change is just this Clippy warning. So let's just add it and amend the previous commit. So it's amend, not amend, amend. Okay, and I think that will be it for this video, because I'm already a bit tired. I don't know if I want to do, yeah, I actually kind of want to do a little thumbnail for this. This has been day 23. This was a long walk until the solution, I guess, but also longest path anti-Dijkstra thing. I don't know, anti-Dijkstra thingy. It's not so bad, anti-distra, but it's not like an anti-dis. Well, it's kind of. Longest path. Let's just call it a boring title, but this is a longest path search. That's what we did. Those colors are very boring. Those are a bit better, but those seem the same. I'm getting the same random. Is it always the same color? Oh, that is good. And also we are walking through a forest, so I guess a bit more green is nice. We can leave the longest path code here, which actually is the only thing that looks nice about this code, I think. And actually, I don't know why we are returning a result here. We can just return U32 because we are not failing it in any other case. So let's just return that. Let's just return that. And okay, like we could have, if we don't find the longest path, it's gonna be 0, but who cares? Who cares about that? Yeah, that looks all right. And I think that will be it for this video, almost 2 hours long. So I have been sitting with this problem for like 5 or 6 hours or something. That's a lot for a single puzzle, but we are in day 23, so it's like it's to be expected that these things are the hardest, and I hope that 24 is not as hard as this one, but there is a chance that it will be, so we have to brace ourselves and face it and see what it is about. But this will be it for this video, and as usual, if you have been, thanks for watching and see you later. Bye bye.